Okay, in order to better compute the Fibonacci number, let's first take a look at the recursive calls that the function is actually calling. So if n is equal to 0, we have only one recursive call. Okay? If n is equal to 1, the function only gets called once also. All right? If n is equal to 2, then we call 0 and 1. The function from n equals to 2, we call n equals to 0, and we call n equals to 1. If the function is equal to 3, we call the function n equals 0 and n equals 2, which then calls the function n equals 0 and n equals 1. Then, if the n is equal to 4, if the input is 4, we call Fibonacci of 2, Fibonacci of 3. But those calls themselves call Fibonacci of 0, Fibonacci of 1, and Fibonacci of 1, and again, Fibonacci of 2, Fibonacci of 0, Fibonacci of 1. And it just keeps growing, right? That's the hard thing. That's the awful thing about what we've done currently is that writing the Fibonacci sequence algorithm in the recursive manner we wrote it is beautiful, but we're computing the same function over and over and over again, and it's so inefficient. So, how do we make this better? How do we make this better? And we can make this better by writing this iteratively, right? So I'm sure the minute that you saw the Fibonacci number, your mind may have gone to recursion, but then if you thought about it for a bit, you thought, hey, this is only a one-dimensional vector. You could implement the Fibonacci numbers very easily using a for loop, and that's in fact what you should do. You could have your base cases here, and then you have your base of the array. You have a base of an array. You declare an array for all the Fibonacci numbers. So you would have to declare it depending on, well, it depends on your language. But you would have to say fib equals new array of n elements of size n times int. You probably could see what language I prefer to use from this statement. But anyway, as long as you have the memory, you could calculate each of the Fibonacci numbers. You say the first element of the array is fib of 0, which is 0. You initialize the second element of the array as fib of 1, which is 1. And then you just iterate through the array and fill out the Fibonacci numbers at every element of the array based on the index. And then once you reach n, you simply return the last element of the array. Simple as that. So what is the running time of this algorithm? It's much better. It's O of n, right? Because the loop right here has loops n times, and you do O of 1 work here. Okay, so the whole algorithm runs in O of n. So the issue is that the recursive algorithm computes the same numbers again and again, and the iterative algorithm is storing the computed values and building from the bottom up to the final value. This is what's known as memoization. Okay, this is a fundamental thing in computer science, that if you know you have a problem with a distinct set of inputs, and you know you're going to calculate one particular instance of the problem over and over and over and over again, you're better off by storing the solution to that problem instance somewhere, and then when you need to calculate that problem instance again, you just pluck the stored solution, right? I mean, it's the same thing you would do in your homework, right? If you would do the same assignment over and over and over again, you wouldn't just manually, like, go from no knowledge and do it out, look through the papers, look through the references, and do the same problem over and over again. No, you would have your solution, you would store it somewhere, and then when the teacher told you to turn in this homework problem for the nth time, you would just copy and paste your previous solution and give it to him, right? So all memoization is the idea in computer science when you have a particular problem instance that you are going to hit multiple times, you should store the solution so that after the first time you don't have to recompute everything. So dynamic programming then is the idea that a recursion can be efficiently memorized. That basically you could use memoization in combination with recursion to get a polynomial time algorithm if the number of subproblems is polynomial in input size. Okay? And we're going to go through instances of that in a moment. Thanks.